Good evening, good afternoon for everyone. Thanks you for joining our event. I am Beraldo Lisenberg from the Santa Catarina State University, and we are starting right now the second talk of our annual event, and is sixth edition. Well, before we start, we have less than 5 minutes video from one of our sponsors, the International Society of Photogrammetry and Remote Sensing, and supported as well from the Geoscience and Remote Sensing Society. Well, can we put the video?
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the sixth edition of the IEEE GRSS Young Professionals and ISBRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISBRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
Okay, thank you for the nice introduction, Cheryl. Well, I will pass over actually to Professor Centeno from the Federal University of Paraná for sharing actually the second talk. Centeno, thank you a lot for accepting our invitation. Please, the room is now yours.
Thank you very much, and welcome everybody for this meeting. I am very happy to take part in this new version of the Young Professional. We worked in the first one, I guess, in Curitiba. There was some others. There were others in Brazil, and I'm always happy. I am not young anymore, but I'm always happy to see a lot of young people working in the field. So today we are here to hear something about the overview of the NASA TROPICS project, CubeSat Constellation mission. This is a very interesting topic, and it will be presented by Dr. Blackwell. William Blackwell received the Bachelor of Electrical Engineering degree from the Georgia University of Technology and the Master and Doctoral degrees in Electrical Engineering and Computer Science from MIT in the United States. Dr. William Blackwell is the Associate Leader of the Applied Space System Group at MIT, where he leads a number of projects involving atmospheric remote sensing, including the development and calibration of airborne and spaceborne microwave sensors, the retrieval of geophysical products from remote radiance measurements, and the application of electromagnetic signal processing and estimation theory. So I am very happy to receive him here, and I want to thank him for the time he gives us, and it's a pleasure to have you with us. As co-chairs, I have two persons from Brazil. One is Marco Ridenti. He is Mr. Ridenti, got the bachelor and master degree in physics from the Institute of Physics at ISP in Sao Paulo, and the doctoral degree from the Institute of Physics at Unicamp. He is currently professor at the University of Technology, Aerospace Technology at ITA, well known as ITA in Brazil, where he develops research in the field of plasma physics and electronic kinetic theory, and also computational fluid dynamics, thermodynamics, and simulation of molecular spectra. Fabrizio Prol, the other member of the chair, is studied cartographic engineering at UNESP, where he also got his master and doctoral degree. He is currently a researcher at the German Aerospace Center, Deutsches Zentrum für Luft- und Raumfahrt, DLR, where he researches themes related to GNSS. So after this brief presentation of the involved persons, I would like to invite Professor Blackwell to talk us about the project and the CubeSat experience of NASA. Thank you, Bill Blackwell, for the presentation in advance.
Thank you very much for the kind introduction. It's my pleasure to be with you and to talk about the NASA TROPICS mission. Okay, let me see if I can share my screen and get the presentation up. All right, can you see the first slide?
No, still not.
Okay, let's see. Let's try this. Ah, okay, I see the problem. How about now?
Oh, yes.
Okay, very good. So I am the principal investigator of the NASA TROPICS mission. And there are a couple of unique characteristics of this mission. This is the first time that NASA is using a constellation of CubeSats. These are very tiny satellites. What the mass is about 6 kilograms. And what we're trying to do with the TROPICS mission is to study tropical cyclones. And by flying a constellation, we can improve what's called the revisit rate, how often we're able to fly over and make a measurement of a storm. And we can capture the dynamics of the cyclone. So TROPICS is an acronym. It stands for Time-Resolved Observations of Precipitation Structure and Storm Intensity with a Constellation of Small Sats. And we're working with a number of different agencies, NASA, NOAA, universities, Wisconsin, Miami, Vanderbilt, and others to pull off the mission. So in this talk, I'll tell you a little bit about why we need to do a better job measuring tropical cyclones and how that will help us as a society. I'll talk about how we implement the mission. You'll see that there's quite a bit of new technology that we are bringing to bear on this problem, which is pretty interesting. We're using a lot of the new commercial space elements for command and control of the satellites and ground stations and operations. So I'll go through that, and then at the end, I'll give just a little bit of a taste of how we generate the products and how we assess performance. Okay, first, let me provide a little bit of motivation on why it is so important to do a better job measuring tropical cyclones from space. As you all know, they have enormous impacts on our daily lives in terms of the damage they can cause, lives lost, property damage. And here's just one example from a couple of years ago. This typhoon Jebi was a very intense storm, resulting in $3.5 billion of damage, many lives lost. And this is just one of many. We have a growing number of these storms that happen every season. So there are more of these coming, and they're getting very intense. So we need to do a better job of predicting what they will do to help for emergency management and disaster management, get people warning so they can evacuate and so forth. So this is one of many examples of these types of very powerful storms. And here, this slide depicts what we're trying to do when we forecast a storm and why it's so difficult. So this is Hurricane Irma, and you see the Thursday 8 a.m. the red dot is the current state of the storm at this time. And we're trying to forecast where the storm will go. That's the black line with the black dots, and how intense it will get over the course of the evolution of the storm. So here at this point, this is a Thursday morning. The forecast was for the storm to hit the eastern part of the southeastern United States and resulted in an evacuation of all those people in those areas. Now, if we move forward in time to Saturday, you see what actually happened. The storm actually went on the left side, the western part of Florida. So we evacuated the wrong side of that region of the country, and we got that one wrong. So now we got to evacuate a new set of folks. And then so the next time that a forecast evacuation warning would be issued, people might not be as attuned to follow those instructions. So it's very important that we get these evacuations right, and it's very difficult to forecast what they call the track of the storm. So we need to do a better job with these forecasts. And the best way to drive those improved forecasts is the measurements that go into the forecast model, these observations that we make from space on a global basis. So that's really driving what TROPICS is trying to do, is improve our fundamental understanding of these tropical cyclones, understand how they form and how they change and evolve and what they might do next. So to do that, we need to measure some fundamental variables that drive the tropical cyclones, cause them to form, and and make the evolution of how these storms change. So first is what we call humidity profile. This is the amount of moisture in the atmosphere as a function of altitude, and we need this in 3 dimensions. And this is because the warm, moist air is really the engine of the storm. It fuels the tropical cyclone. The air rises through the storm and then starts to circulate, and that's really what makes the storms go. So we need to measure the humidity profile. We also need to measure the temperature profile. So the plot on the right here shows a cross-section of the eye of the tropical cyclone. And just to give you an example, so the red color is a warming aloft in the eye at about 10 kilometers. And that warming, we can measure that and relate that to intensity of the storm with very high correlation. This is one of the markers that allow us to say something about intensification. So we need temperature profiles as a function of space. That's another 3-dimensional quantity. And we also need to measure precipitation. So here's an animation that shows the spiraling tropical cyclone with the rain bands coming off from the center. And there are various amounts of the red indicates very high scattering off the ice and the cloud top. So we can measure that and say things about the asymmetry of the storm, which is also an indicator of intensification, and things like that. So to summarize the key observables, we need to measure temperature, humidity, and precipitation in 3 dimensions. And also the 4th dimension is time. So we need to measure these very rapidly as the storm evolves to capture the dynamics on the order of minutes. And we need to feed all that data into the forecast models to improve our predictions of what the storm will do. So that's really what we need to do from an observation standpoint. And the other challenge is the sheer number of storms. So here's one example from a couple of years ago where we had, looks like 9 storms either brewing or forming in a single day over the entire globe. Right? So we need to make these measurements not just in the localized region, but over the entire global tropical cyclone belt to try to track the storms that are either raging or about to form and intensify. Right? So it's a truly global observation problem, which motivates a space-borne network of instruments. Okay, so there are a number of ways that we can measure those key observables that we need to characterize tropical cyclones. Ground-based radar are very sensitive to the precipitation, but we don't have those out at sea, so we have a problem of coverage with the radars. There are a number of 1 or 2 limited radars from space, but again, they have very sparse coverage. So the issue there is we need synoptic coverage. We can drop instrumentation from aircraft, and again, there's a sparse coverage issue there. We don't have enough aircraft to cover all the storms. We can measure ocean surface winds. There's a new mission that you may have heard about or will hear about called Cygnus. It's designed to measure the winds of the ocean near a storm. And that's good, but it doesn't give us a sense of what's happening inside the storm. We need to penetrate inside the storm to measure the vertical profiles of things to get the thermodynamic picture of the storm. So that's one piece of important information, but we need more. The visible and infrared imaging and sounders we can fly from geostationary satellites that can stare down at a particular point on the Earth. But we have, they're limited in geographical extent. We can only measure a certain basin of the storm. And most problematic is those sensors can only image the cloud top, so they can't see below the clouds to understand what's happening inside of the storm. So passive microwave sounding is kind of a nice compromise. It gives us everything that we need. We can penetrate the cloud top. We can fly these sensors in low Earth orbits and get synoptic coverage. We can measure temperature, moisture, rainfall with good enough accuracy to characterize the storms and measure those variables under clouds and over on a global scale. So it's a good sweet spot for this constellation that TROPICS is intended to achieve here. So if we look at all these different kinds of observations and ask the question, well, which of these are the most impactful, have the biggest impact in the forecast, we get this bar chart. So what I'm showing you is the impact. So a bigger bar to the right means it has more impact to get a better forecast. And at the top of the graph, as we just talked about, we have the microwave data. The humidity and precipitation is the best source of data. And number two is the microwave temperature. And underneath that, we have infrared, dropsondes, wind speed indicators, and things like that. And the reason the microwave is at the top of the list is its ability to penetrate the cloud deck and measure phenomena that are going on inside of the storm. That's really critical to understanding what's going on with the storm. Okay, so how do we measure a vertical profile with an instrument that's flying in space? And the secret to that is taking advantage of what are called atmospheric absorption lines. So there is a line that, due to oxygen, that happens near 118.75 gigahertz. And the nice thing is that if we measure the upwelling radiance that's emitted by the atmosphere of the Earth near that frequency, we can use the fact that the opacity changes as we move away from the line center. That's this, I hope you can see my cursor here if I move this around. As we go off the center of the line, the zenith opacity decreases. And that does something very convenient for us. So if we measure this radiance that's emitted near the line, we measure the contribution of the upper part of the atmosphere. And as we move away from the line, there's more, the atmosphere is more transparent. We measure near the surface. So there's this gradual vertical dimension. As we move away from the line, we're measuring near the surface because there's a lot of transparency in the atmosphere. As we move closer to the line, we're measuring higher in the atmosphere because there's more opacity blocking the lower part of the atmosphere. So by walking up towards the center of the absorption line, these are these channels that we fly in tropics. So there are 8 channels off the line. We get various vertical distributions of temperature using this absorption feature and this opacity that drops off as you move away from the line. So that's how we do the vertical profile, is measuring these different channels off the line center. Okay, so, and we do the same thing for water vapor, by the way. There's a line at 183.31, so we can get a vertical profile of moisture. So that we've been flying weather satellites to make these measurements for decades. And in the US, we have the National Oceanic and Atmospheric Administration that has a very small network of very capable, but big and expensive satellites. Here's one example. Here's a person leaning over the table here for scale. That flies a number, there's about 5 of these instruments that fly on these very large satellites that make these measurements and other measurements to allow us to do the profiling. So the drawback to these kinds of traditional satellites is that they're very big and expensive, and they take a long time to build and test and launch. So as a result of that, we have a very small number of these in service. So there's about 3 or 4 of these satellites in various orbits. And what that means is that if there's a storm that's currently active, one of these low Earth orbiting polar satellites will fly over, and then we have to wait about 4 hours or so for the next satellite to fly over and measure it again. And the problem is that the storm, is evolving on the time scale of, say, tens of minutes. So there's a lot that we're missing in that 4 hours. So that's a real problem. We need to improve this 4-hour revisit rate, and that's really what TROPICS is designed to contribute. So we've been working on this program, this type of problem for almost a decade now. And one of the things that happened, I was involved with some early aircraft observations of tropical cyclones that showed that we could make useful measurements at 118.75 gigahertz near that oxygen line. And we can make the measurements even sensing through the cloud top. So that was good information that would allow us to try to design and build radiometers that operated at 118 gigahertz as opposed to the traditional band, which was 60 gigahertz. And that would allow us to fly smaller antennas and potentially host these instruments on very small spacecraft relative to what we've been flying. So this slide gives you the evolution of the technology development and maturation that we've been going through to make tropics a reality. So we started by building and testing very small receivers and trying to understand how we would fly these systems on a very small CubeSat. The NASA Earth Science Technology Office has invested in some technology maturation for some of the key components of that. This is an intermediate frequency processor. This component actually produces that channel set that I showed you, those 8 channels near 118.75 to do the vertical profiling. Those are all split and measured in this particular component. And we've flown some technology demonstrations over the last 5 years that have showed that this is in fact a viable way to make the measurement. Micromass 2A launched in January that proved for the first time we could do temperature and moisture profiling from a CubeSat. And then TROPICS is aiming to fly a constellation of these types of satellites to give us 40-minute revisit rate instead of 4-hour. So this is where we've come. Now I mentioned the Micromass 2A CubeSat. This was a huge step forward. Again, January of 2018, we launched this, and for the first time, we showed that we could get temperature profile data and water vapor profile data and imaging from this very tiny, $1 million class satellite instead of a $2 billion class satellite. And the data that we have looks very good in comparison with ATMS, which is the sensor that's flying on the NOAA, large, expensive satellite. So there's a paper down here that recently came out that shows some of the data that we get from Micromass 2A. It'll be very useful for these kinds of studies at very low cost. So the obvious next step is that if we can make an instrument that can make this measurement at low cost, let's fly a lot of these and put them in a constellation, and then we can improve the revisit rate and get that 4 hours down to half an hour or so. So that's really the motivation behind TROPICS, is to fly a lot of these satellites. So TROPICS is a NASA Earth venture.
Just sorry for interrupting. People are just complaining that the screen is not appearing. Would it possible to share it again? The presentation again? Yeah. Just sorry for interrupting.
No, I'm glad you told me that. So can you see the screen now? Is that better or worse? Can you see the screen now?
Yeah.
Okay, should I go? So what I did was I took it out of full screen mode. So did that seem to solve the problem?
Geraldo?
Yeah, I think it's okay, because if you share it, the borders are not appearing at all.
Okay,
so
let me try.
If possible.
Let me try one more thing here. Okay, let me do entire screen. This. Okay, how about now? How does that look?
Wonderful.
Okay.
This is okay.
Fantastic. Thanks very much for alerting me to that fact. All right, so here we go. So good timing, because I'm just now starting to talk about the TROPICS mission. So this is an Earth Venture mission selected by NASA in 2016. This is the Earth Venture Instrument 3 selected, and this is managed out of the Langley ESSP office. So I'm the principal investigator, as I mentioned. Scott Brown out of NASA Goddard is our project scientist. We've got a very capable team behind us on the science side and on the instrumentation side and on the spacecraft side. So we've got a company, Blue Canyon Technologies, that's building essentially 2/3 of the spacecraft is the bus, and it's built by Blue Canyon. And MIT Lincoln Laboratory is building this rotating payload. So the way we get coverage of the tropical cyclones is, as these satellites fly, this radiometer payload on the end of the satellite is spinning once every 2 seconds, and that results in a swath across the Earth to make the measurements. By flying 6 of these, we get the global coverage of the tropical cyclone belt, of the temperature and the moisture, and so forth. So here on the lower right is a photograph of the 6 flight units that we have already finished and tested and delivered, and they're waiting on a flight the launch for flight in early 2022. So NASA is responsible for finding those launches, and they're out doing that now in anticipation of launches in early 2022. So let me give you some details on how the mission is put together. And from NASA's point of view, this is really a science mission, it's not a technology demonstration mission. This is a mission that is intended to go after and improve our understanding of basic science properties of tropical cyclones. And what we're trying to do is really relate those key observables that I mentioned before, the moisture and the temperature and precipitation structure, to intensification of storms. All right, and so what I'm showing you down here in the bottom of the slide are some things that we would like to measure. So this is in the bottom left image, the bottom left panel here is rainfall as a function of radius. This is radial distance from the eye of the storm on the x-axis, and time evolution in days on the y-axis. So you can see there's a very calm eye here on the left part of the figure. And as the storm intensifies over the course of a few days, it really starts to rage here. So here's the precipitation, and you can see rain bands spiraling off from the eye. And this is what we need to measure with tropics: is how hard is it raining? Is the storm asymmetric, and so forth. So here is a simulation that the second and third panels here show simulated observations near 118 gigahertz and near 206 gigahertz, which is our highest frequency channel. And we can, in fact, recover this information, the rain bands spiraling off to temporal resolutions of about 30 to 40 minutes. So this is going to be great information to relate these features and improve forecasting. On the right is another example of the warm core. So this is a slice through the center of the storm. And I'm showing you essentially temperature is a function of altitude. It's shown as channels in the that span the vertical space of the storm. And here's the eye, and you can see there's this warming aloft in the storm. That's the warm core anomaly that I mentioned earlier that tells us something about the intensity of the storm. So here are the objectives. We're trying to relate these markers to intensity and ultimately to improve our predictive models for forecasting track and intensity. So that's what we're trying to do from a high level with the TROPICS mission. So here's how the mission is architected. So as you can probably imagine, we have a network of ground station antennas sited on the globe. So we're flying along. So there are 3 orbital planes with TROPICS. So there are 6 CubeSats. We fly 2 of them in 3 orbital planes. So if you look carefully at this picture up in the upper left, you can see the ground tracks, 2 satellites in each of these orbital planes. And that gives us coverage spread out over this tropical cyclone belt from about plus minus 37 degrees latitude. So we have antennas located in Dubai, Hardabeestok, and Singapore. We can periodically downlink the data down to the ground and get it out to the user community. Blue Canyon, in addition to building the spacecraft buses, are also handling mission operations. So they're controlling the satellites for us and commanding them to get data down to the ground. We have a science operations center at MIT, and our partners in Wisconsin are doing data processing before the data is then disseminated out to the general public. So everyone will be able to access the data from TROPICS for free. Okay, so one interesting part of the mission is how we selected the orbital configuration. So you might be thinking, well, why do you need 3 orbital planes and 2 satellites per plane? And how did you pick the inclination of the planes and those kinds of things? So that's all determined by where the tropical cyclones form. And here's a picture over the last 30 years or so of tropical cyclone tracks. And you can see there's almost never storms right on the equator. So they're about 10 plus or minus 10 north or south of the equator. And most of the storms happen at about 20, plus 20 or minus 20. So we can actually use that information to optimize the orbital configuration. So if I take that picture and integrate over longitude, here's what it looks like. And you can see that there's almost nothing happening near the equator. Most storms form at about 15 to 20 latitude, plus minus. So we can optimize the configuration of the constellation to put the best sensitivity on these peaks. So almost all tropical cyclones occur within plus minus 40 degrees latitude. So there's really no reason to have the constellation measures, above plus minus 40 because there aren't any tropical cyclones there. So that's why we have this 30-degree inclined near equatorial orbit. So here's the plot that I just showed you, the storm frequency. And by tilting the inclination of the orbital planes, what we can do is we can get the best sensitivity revisit rate to line up exactly with these storm frequency peaks. And this happens when we have 6 satellites and 3 planes that are inclined at 30 degrees with an altitude of 550. So this is a sweet spot that lets us line these up and gets us median revisit rates that are about 40 minutes over the entire global constellation on the median. So that's a nice artifact of how we do this. So here's a slide that summarizes the performance of the spatial resolution. That is, how big is the footprint we get on the ground as we fly over the storm, and how good is our temporal revisit, which is one of the key mission drivers for TROPICS. We want that to be as good as possible. So first, let me compare the spatial resolution of TROPICS to ATMS. One question you might have is, how do you get useful spatial resolution from such a very tiny satellite? And the answer to that is, well, most of the payload, when I show you pictures coming up, the payload is dominated in size and volume by the antenna. So we keep the antenna as big as we can and shrink the electronics around it. So we keep the antenna size as large as we can to improve the resolution. And we're also using 118 gigahertz for temperature as opposed to 60 gigahertz, which ATMS is using. So when we do that, we see the resolution for TROPICS is as good as or better than ATMS for more orbital altitude. So for temperature, we got 24 kilometer footprint diameter at nadir, ATMS is 33. We've got 16 kilometer for moisture, ATMS is 17. At our 90 gigahertz imaging channel, we have 30 kilometer resolution at nadir as opposed to 33. So these are very good numbers, especially when you consider it's a very tiny satellite. And our swath is over 2,000 kilometers wide to get the global coverage. So the spatial resolution is actually quite good, even though it's a very tiny satellite. Now, with respect to the temporal resolution, what I'm showing you in the plot on the bottom is the mean in blue, median in green, and a weighted fraction. This is how often we have to encounter a large gap bigger than 2 hours. That's in this yellow color. And I'm showing you that as a function of how many satellites we fly in the constellation. Okay, so we have a requirement on TROPICS. Our baseline mission must produce median revisits that are better than an hour, 60 minutes. So we want to pick something that's below this lower dashed line. And our threshold is 2 hours. So we want to be extra certain that we are below this second dashed line. So our baseline mission configuration is shown in the green shaded rectangle. We're flying, again, 2 satellites in each of 3 orbital planes, which lets us get we achieve the baseline with some margin. And we can even tolerate the failure of a couple of CubeSats and still meet our performance with the green curve still below this black curve, even with 4 satellites. So we have a little bit of redundancy in the constellation. We can lose a couple of units and still meet our requirements. So you can see there's a very rapid fall off with up to 4, and then it's a gradual decline once you get back past 4. So it's a bit surprising that even with just 6 satellites, we can get this very good performance. And part of that reason is the orbital configuration that we chose. That 30-degree inclined orbit is optimized for cyclones. So we have a requirement to collect data over the course of a year. So, and I showed you that we need 4 of our 6 satellites to operate. So if you do the reliability analysis, there's a 90% probability that we have 4 satellites operating after 1 year. So that gives us confidence that we'll be able to fulfill our mission of a science collect period of 1 year. Okay, so that is kind of the overview of the constellation. Now let me give you a little more details on what the radiometer is and how we build that and how we test it and how it works. All right, so here is more details on the CubeSat that we fly. So this is what we call a 3U. 1U is essentially a 10 by 10 by 10 centimeter cube. that we can aggregate together through our 3U means essentially there's approximately 30 centimeters length. It's 36 centimeters in the long dimension and 10 by 10 in the other dimensions. So again, I mentioned this is very small. So it's a 6 kilogram mass, and the orbit average power that we consume is about 15 watts. To compare this with the ATMS that you saw before, it's about a 100 kilogram instrument and 100 watts. So it's much less than the ATMS instrument. So even though this satellite is very tiny, it still has a lot of functionality and performance. So there's a solar array that actually rotates to track the sun. We can rotate this bus in the roll angle to also track the sun and to point our antennas at the ground stations. On board the satellite, there are 2 star trackers that we use for attitude determination, so we can know where the satellite and thus the radiometer where it's pointed to very high precision. Let's see here. We've got reaction wheels. We have to keep the spacecraft stable as all these things are moving. The array is turning, the bus is rolling, the payload is spinning. And while that's going on, we need to keep the spacecraft stable. So the reaction wheels and the torque rods do that. We have GPS for location, inertial measurement units to help with that, and so forth. On the payload side, so remember this is rotating at 30 RPM. Once every 2 seconds, it rotates across the Earth and across cold sky. This is about 8.5 centimeters across to give us the spatial resolution I mentioned. And we have 12 channels from 90 to 205 gigahertz to measure over the oxygen absorption line and the water vapor absorption line. And the last interesting thing about this is how we calibrate. So there's an onboard noise diode that we can turn on and inject into the front end to give us 1 of 2 calibration points. We need 2 calibration points to derive the absolute radiance from the radiometer. So we use the noise diode for 1 of those, and we look at cold sky away from the Earth to get the second calibration point. So that's how we calibrate, with noise diode and cold sky. And all this folds up into this configuration and slides into a dispenser for launch. So we pop out of the dispenser once we're launched, the solar array unfolds, and then we start to spin the radiometer. So I hope this animation comes through. So what I'm showing you here is that I'm fixing the payload just to make this easier to view. In reality, the payload is also spinning, but this shows you that the spacecraft bus is rolling and the solar array is also turning. So this is designed to keep that array on the sun as the satellite orbits the Earth. And by doing it this way, we can use smaller solar arrays, right? Because it's always pointed at the sun when the sun is in view. And that helps us keep the satellite small and therefore reduces the cost. That's kind of a neat feature. So the payload is actually also turning as well. I'll show you a video of that a little later. Okay. So I mentioned earlier that we can measure in the infrared, we can measure microwave, we can measure visible. So I wanted to give you a little bit of intuition on why we use microwaves and where in the spectrum we are measuring. So again, I mentioned the oxygen absorption line at 118 gigahertz. There's additional lines over here at 60. So ATMS uses these lines near 60, 50 to 60. TROPICS uses 118. We have an imaging channel near 90 gigahertz. Water vapor sounding channels near this line at 183.31, and an imaging channel at 205. And the microwave is really nice. As I mentioned before, we can penetrate those clouds and see the underlying thermal structure below the clouds, which the infrared and the visible cannot do nearly as well. So that's why we're motivated to use microwaves for TROPICS. Here are some details on the 12 channels that we fly. And again, these are all chosen to give us the spacing away from the absorption line that I talked about earlier. So we have some channels that are near the line center. So channel 8, for example, is very close to the center of the 118.75. And then we walk away gradually from the line center to 114.5 gigahertz for sensing near the surface. Same thing for the 183 line. We've got a channel near 183 and channels that gradually walk away from the line, resulting in a channel 7 gigahertz off the line. And then the channels 1 and 12 are imaging channels. Other things in the table, I'm showing you the beam width. This is how broad the antenna beam is that gives us our spatial resolution. Again, the 24-kilometer spatial resolution for temperature, 17 for moisture. And the sensitivity, what we call the noise equivalent delta temperature, is better than a Kelvin, and in some cases about a half a Kelvin for the channel. So we need that sensitivity to be able to capture the signals that are being emanated from the storm, and we can relate that to temperature and moisture. Also, in addition to, we have a very narrow antenna beam, but we also have very low side lobe levels, and we need that because we can't have the image perturbed by what's going on outside of the field of view. So we have a requirement for very low side lobe levels, and our antenna system helps us do that. 97% beam efficiency, which is extremely good for this kind of an antenna. So we've built 7 of these spacecraft and tested them all, and happy to report that two pieces of good news. One is that they all meet requirements, and number one. Number two is they're all very similar to each other. So this is the vertical profiling. Our requirement is 2 Kelvin, RMS uncertainty, and simulations with using our NE delta T and calibration error show that we're down at about 1.6 or 1.7 Kelvin, so much better than the 2 that's our requirement for temperature. And for moisture, our requirement is 25% RMS uncertainty, and we're about 17, 18. So very happy that the satellites are performing very well. Here's another shot of the 118 gigahertz weighting functions. I went through this before. Just wanted to point out here that the weighting functions actually change as the angle of the observation changes. So remember, the radiometer is scanning across the Earth. So we have some observations that are as high as about 55 degrees off of nadir. So the weighting functions change a little bit when we scan across. We have to account for that deviation. We can do that just fine. Here are the weighting functions at 183. This is the water vapor channel. And again, we have a nice coverage vertically from the surface to about 10 kilometers for that water vapor profiling product. And again, the line center is 183.31. Okay, so with those measurements, we have 5 core science products that we derive from TROPICS. I think I've talked about some of these already. The temperature profile and the moisture profile I've discussed. We can also measure, with some utility, instantaneous surface rain rate. We measure the scattering off the ice in the clouds, which we can relate to rain rate. And we can also measure 2 intensity products. These are derived from that warm core anomaly, the temperature anomaly in the eye, minimum sea level pressure, and maximum sustained wind, which tells us essentially how intense the storm is. So we've been simulating all the performance for these products, and they look very good based on the pre-launch testing of the instrumentation. So we're very happy about that. And these are on par with the ATMS-like sensors. Not quite as good as ATMS, because ATMS uses the 60 gigahertz, which gives more penetration to the clouds than 118, but still very good. Okay, so let me give you some details on the hardware, how we actually built the instrument, some of the details with that. So here again, so now I'm showing you the animation of the scanning radiometer payload. It directs the antenna beam across the Earth as it flies, and then away from the Earth to calibrate against the cold sky background. So here's the kind of the schematic of that. So we scan across the Earth. Remember, this is a 2,000 kilometer wide swath. And then we keep scanning away from the Earth into the deep space. Okay, we make a calibration measurement. This is our cold calibration. Then we turn our noise diode on to get our warm calibration, and we do that every time we scan. We have to be careful that we don't accidentally measure the sun or the moon, so we know where they are, so we can make sure that we choose these sectors so that we don't measure the sun or the moon or our solar array. So we know where these things are, we can avoid them. And over on the left-hand side are just some details on how many spots across the swath are. We take 80 samples. The integration time is about 8 milliseconds. And then here's some more information on the full width, half max antenna beam width and our resulting nadir resolution that I've already talked about. Okay, so I mentioned that we're using noise diodes for calibration. That's a relatively new thing to do. We do have some prior work on this from the GPM mission, is a mission flown by NASA, a global precipitation mission, And one of the instruments on the GPM is called the GMI, the GPM Microwave Imager. And they flew noise diodes and have been since this was launched in 2014. So we've got about 5-6 years of data on noise diodes and how stable they are. And the news is good. So with GMI, most of the noise diodes are stable to better than 1/10 of a Kelvin. That's incredibly stable, even better than the traditional onboard calibration blackbody targets. So we have very high confidence that our diodes are going to work, about this well. So here's a chart that shows a comparison of noise diode drift against the drift in the internal blackbody calibration targets. And this is showing us that the blackbody calibration targets are drifting more than the noise diodes because of thermal. The sun can get on the target and warm them up, and you have thermal gradients on the targets. And the noise diodes are good enough where you can actually detect that warming. So again, very, very good information from GMI. The noise diodes are a viable way to do calibration. It's very stable over many years. So we hope to see that same level of stability with TROPICS. All right, so here are some details on the instrument. So as I mentioned before, we're motivated to keep the antenna as large as we can because that improves our spatial resolution. So that essentially drives the volume of this payload cube. So we take as much volume as we can for the antenna, and then we tuck all the electronics around the side and the back of the antenna. So we have our G-band receiver for water vapor. We have our what we call the WF band. This is for the temperature and the imaging. This is the 90 to 120 gigahertz receiver here. This is the intermediate frequency processor that I mentioned very briefly earlier to do the channelization near the oxygen absorption line, and some supporting electronics. We have a local oscillator source. We've got a control data handling board. Here's the scanning assembly and slip ring to get the data back from the payload to the spacecraft bus. It goes over the middle of this and through a slip ring back to the bus. So there's a motor that turns the payload, and some electronics that run all this. This essentially just snaps together, and the outer plates go on the payload cube, and it's a very compact but high performance radiometer system. It's very miniaturized. All right, so here's some actual pictures of the flight hardware. The antenna is very interesting because we have two bands, and we have a single parabolic reflector that need to share that. So we have, if you look carefully, you can see there's actually two feed horn antennas. There's one here, and there's one back here, and there's a polarizing wire grid dichroic that allows us to split this beam. So one beam goes through the dichroic, and the other beam is reflected off the surface, and it hits this parabolic reflector and then the Earth. Okay, so the challenge of doing this is to make all this happen and getting a very narrow beam and very high beam efficiency. So Thomas Keating was our partner on this one. They did a fantastic job making and testing these antennas. They work great. Here's a coin for scale. It's very, very compact assembly. Here's the receiver. UMass Amherst Radio Astronomy Department is very good at building these. So here's a very compact, low power RF front end that works from 90 to 120. I mentioned the G-band receiver down here in the lower right is about the size of a deck of playing cards, and it's state-of-the-art performance in terms of its spectral passband and sensitivity. Here's the scanning assembly. You can see the hole for the slip ring. I showed you this is the IFP, the channelizer for the temperature sounding, and the payload control and data handling board with the hole there for the slip ring electronic to go through the middle of that. And here's the final built-up actual radiometer hardware. This is the same piece of hardware, just from two different perspectives. You can see the G-band receiver. Again, in the middle of all this is the antenna. The scanning assembly at the bottom, and all the electronics kind of around the sides and the back of this, so we can maximize the amount of antenna aperture we have. You can see there's some heaters on here to try to keep things thermally stable and controlled, and so forth. Okay, and it's, we worked really hard to make the radiometer small, and we were very pleased by how well it performed even after having undergone that drastic miniaturization. So we've got, certainly the highest channel density. We have 12 channels in this very small, compact volume. And I showed you that we're able to compete with ATMS on spatial resolution, even though this is a very small package. The antennas are so good we had to improve our test facilities to even measure the side lobes because they were so low. So we were able to do that with very high precision. The NA delta T for the water vapor channels is among the best that's ever flown for any size, especially for a CubeSat. And I'll show you coming up here, we developed some custom calibration ground support equipment to do the testing of the calibration accuracy, and that is very high fidelity and among the best in the world right now for that. And here it is. So what we needed to do was test our payload. So in the middle of this, there's our payload that'll spin around over the course of the test. So all of this equipment goes inside of a thermal vacuum chamber to simulate the environment of space and to simulate the Earth and the cold sky. So we simulate those scenes where there are actually 3 targets behind all of this mylar insulation, 1 down at the bottom and 2 on the upper sides. So as the payload is spinning in the TVAC chamber, we can make measurements of these 3 targets and compare our measurements with what the instrumentation on the targets is telling us and say something about the calibration accuracy and the stability and the sensitivity of the radiometer. So here's the electronics that control all that, the temperatures of the 3 targets and the temperature of the payload. Right, so its temperature will be changing over the course of an orbit as well. So here's the kind of thing that we do in the TVAC chamber. So we're continuously changing the temperature of the payload and the targets. So this yellow curve is that we're stepping through a series of targets to simulate what the Earth would look like for various temperatures. And we have all kinds of different combinations of payload temperature, Earth temperature, cold sky temperatures, and so forth. So over the course of a couple of weeks for each of these payloads, we're able to put together a very high fidelity picture of the stability of the radiometer and how it works over a wide range of temperatures that we'll see on orbit. So I worked very hard to automate all this processing so we can essentially put it in the calibration chamber and have all this run in an automated fashion over the course of many days of calibration testing. So that worked very well. So at the end of all that, what we're trying to do is measure the response function of the calibration. And we want to do that as faithfully as we can to how the system will actually fly in space. So over the course of the payload temperature changing, over the course of an orbit, the payload will change over about 6 Kelvin, plus minus 3 Kelvin. And that will depend on what season it is, what the solar beta angle, and so forth. So we've got to convince ourselves that the noise diode temperature is a simple, repeatable function of payload temperature that we can use to help us calibrate the sensor, whatever the temperature of the payload is. So once we do that, we can show that our overall calibration accuracy is very good. Our requirements are shown here in the red dashed, and we do much better than requirements for accuracy. This is for a temperature sounding channel and for a moisture sounding channel. So we're very pleased to see that the radiometers are performing very accurately in the TVAC chamber. And finally, just some nice animations. So this is on the left is the engineering qualification unit. If you look very carefully, you can see the array is gradually turning, the payload is moving, and when it's on orbit, this bus will also be rotating as well. So you have 3 things moving: the array, the bus, and the payload will all be rotating. And they're actually reaction wheels spinning inside of the bus to counteract all that motion. So the Pathfinder mission we're actually going to fly this in advance of the Constellation mission in June of 2021. It's going to give us a great opportunity to check out everything, right? To check out the radiometer, the ground processing, our ground network operations, science algorithms in advance of the main Constellation mission. So we'll start launching these 6 spacecraft in January of 2022. And again, NASA is responsible for those launches, and they are working that now. So we've got 7 spacecraft that we've built and tested, essentially ready to go for 4 launches coming up in 2021 and 2022. Okay, so the last thing I wanted to mention here was some performance. So now that we've built these satellites and made all kinds of measurements of the radiometric performance and characteristics, how well do we think that our products will be? And what can we do in terms of getting the user community ready to adopt the use of our products? So just a few comments on that, and then I'll summarize. Okay, so I mentioned that we had this 2 Kelvin RMS uncertainty requirement for our temperature profile. So what we do to evaluate that before we launch is we take an ensemble of many tens of thousands of profiles over a wide variety of atmospheric conditions, clouds, light rain, and so forth. And we simulate what TROPICS will observe given the instrument properties that we derived over the course of testing. And we get this black dashed line curve. So here's our best guess of the uncertainty of our product, given all the characteristics that we know about the radiometer. And this is the source of that 1.6 Kelvin that I mentioned before. This is temperature profile. So again, we want to be to the left of our green baseline requirement curve. And this is moisture. So we want to be better than 25%, and we're at about 17. So that's how we do all this. We're using the TVAC calibration data and this ensemble set of profiles. For rain rate, we do the same thing. So we're trying to characterize the RMS uncertainty in millimeter per hour over as a function of how hard, the intensity of the rain rate. And we want to be better than this, this green curve here, and we're much better than that. So we're trying to, the ratio of this number to that number is our percentage. We're trying to be 25% or better, and we are. So that's good. So one of the last things I wanted to talk about is the derivation of the warm core anomaly. And there is one challenge retrieving this. So what we're trying to do is, again, measure the temperature in the eye of the storm. Okay, that's a central part here. And when there's a very intense storm, what happens is that the eye actually clears out. The clouds, if you see a picture from space of a raging tropical cyclone, it's a very clear eye. And that's what you see here. We get a very strong temperature anomaly that we can relate very accurately to intensity. And here's how that works. So here's, so the anomaly there is about 6 Kelvin for this particular channel. And there's a very strong correlation between the anomaly and brightness temperature and the pressure anomaly. So we can actually derive this minimum sea level pressure very accurately for this case because it's very intense, very clear eye. We get a very strong anomaly. But that doesn't always happen. So when we have a weaker storm, what happens is there's clouds that shroud the top of the eye, and they have so much ice in them, and even our microwave channels are perturbed by some of this ice, heavy convection, as the storm forms, and that creates problems sometimes. If it's a weak storm with a lot of ice in the clouds, the anomaly is somewhat muted, right? So we're seeing attenuation of that anomaly due to the ice, and it completely masks the warm core for this particular channel. And what that does to us is it gives us a false reading. So the truth is down here on the X, but we measure something up there. So there's the big error in our MSLP because of this ice shrouding of the clouds. So this is one of the challenges that we're working on now. And the way we're trying to get around that, one way is that this is just a single channel anomaly shown here, but we can use multiple channels to try to get a better read on some of the shrouding, use our high frequency channel to flag when there's strong attenuation. So this is one of the things that we're working on now to try to improve is this warm core anomaly relationship when there's ice in the clouds above the storm. Okay, another thing that we're trying to do is something called an observing system simulation experiment, which is to say if we did have TROPICS up and operational and had all this great data, how would it impact the forecast? So we can actually simulate the forecast of track and intensity MSLP and simulate TROPICS and ingest that into the forecast model and ask the question, how much better would the forecast skill be as a result of having this data? So a positive number means that we have improved skill relative to without the data. So these are some NOAA results that show that we have, again, this is a forecast lead time from essentially 0 hours all the way out to multiple days. And we have improved track forecasting, over every time scale, all right? And improve intensity forecasting up to about 36 hours. So this is very promising that we'll be able to improve certainly the track and even the intensity, which is a very challenging thing to improve with forecasting. We can do that up to about 36 hours, we think. And this is kind of a preliminary study here. So there's some opportunities to improve this even further. So we're very happy about the potential for the forecast improvement using TROPICS data. Okay. So with that, I will wrap up. So you can tell we're getting very excited about these launches coming up for TROPICS in the next couple of years. We can now use a constellation of relatively affordable small CubeSats to essentially scale up what we're already doing now with the NOAA operational enterprise to give us much better revisit rate that we need to capture the dynamics of tropical cyclones. We're going to be measuring temperature, humidity, precipitation, and storm intensity. We've been working really hard, as I talked about, to do simulations with proxy data to verify our performance and try to optimize, identify areas where we need to improve. Like I showed you the example of the warm core with a weak storms, so we're trying to actually improve performance there. To see how good we will be and see where we need to improve, and to kind of judge the impact that we'll have and help users try to make sense of our data when it becomes available. So everything has been built, completed, ready for some launch. So the bullet there is a little old, so we were actually ready. January of this year, we were ready to go. We were waiting on NASA to get us 4 launches, 1 in 2021 and 3 in 2022 to launch the constellation. So with that, I will stop, and I'd be very happy to answer any questions or elaborate or clarify on anything as you would like. So again, thanks very much.
So thank you very much, and I really enjoyed the presentation. It's very fresh news from the front. And now I will open the session of questions, and with the support of Marco and Fabrizio, we will start making some questions from us and also from the people that are listening through the internet. And I guess people feel free to ask. Please, if possible, ask in English. We can give this to Bill, but if it's not possible, you can make this question in Spanish or Portuguese. We can translate it online. And how about? Let me first start with my curiosity, satisfy my curiosity. These satellites are in Ecuador, you said, and are they stationary in relation to the Earth? Are they always moving at different points? Are they always at the same point above the Earth?
No, they're going to be orbiting the Earth. So they're going to make one revolution of the Earth every about 95 minutes. They'll make one. And in addition to that, they're going to be moving very slowly with respect to each other. So the 2 satellites, even though they'll be in the same orbital plane, over the course of many weeks, they'll actually start to drift with respect to each other.
Oh, okay. Oh, then Marco, Fabrizio, do you have some question? Marco, feel free to ask.
Okay. First of all, I enjoyed to listen this lecture. I was really impressed. It's a very interesting topic, and studying cyclone. It's an exciting topic, subject of this mission. The tropical cyclones, and I like the way you were very clear about the mission and the satellites. I've read your paper, but there's no details about the satellite. I saw it's very tiny. It's a very tiny CubeSat, but with high technology. I was impressed by the way you managed to improve the antenna, and also there are 2 rotating axes, so you have to. I think that's not trivial to control the attitude of these satellites. That's another question. But the first question I have here is. Probably that's the first time you are using a constellation of satellites. I know you have a lot of experience in data retrieval from microwave sensing, and my question is if does the data retrieval of physical quantities will be based on well-established methods, or we will need the development of new methods and strategies? What are the main challenges in terms of that analysis?
Yeah, okay, that's an excellent question. All right, so from a perspective of one of the satellites in the constellation, the processing is exactly the same as we've done it before. Okay, the frequencies, we have to deal with the frequencies and the spectral passbands of the sensors, but we know how to do that. All right, that's on a satellite by satellite basis. But your question is different. You're saying, look, we have a constellation, we have a system of these 6 satellites, how can we optimize the use holistically of the sensors? And that's where it gets interesting, because for example, we need to make sure that there are no biases among the satellites, right? If there's some calibration bias between the satellites, that will manifest itself as an error in the data product. So we don't want that. Okay, so we've got to make sure that the satellites are stable and interconsistent from a calibration standpoint. That's number one. And we need to make sure that there aren't any drifts. So second order effects, right? So they have to be stable over time as well, right? So I think the challenges of the constellation have to do with calibration artifacts. The generation of the products and the radiances, I think, is fairly straightforward and can be handled in the same kind of enterprise that we've used before. But the data taken together, we have you know, kind of different elements in the constellation. We have to make sure that they're all, you know, interconsistent from a calibration standpoint, I think, is the biggest challenge.
Okay.
I guess another thing that we got to be careful about is that, so satellites are going to be viewing a given scene at different viewing angles, right? So we have one satellite that'll fly over in one orbit and view a storm, and then there'll be another satellite that's way over here and looking at a very oblique angle. So we've got to be very careful that we handle these different viewing geometries, you know, correctly. That's the other thing.
Great.
So, Fabrizio, do you have something to ask?
Yes, thank you very much for this great presentation. I have a couple of questions here, but if the chat also has any questions, please feel free. So one thing that I'm interested to know is how much computer capabilities are required for the data simulation of this data in, let's say, in a global scale with this three-dimensional VAR or the 3D VAR. I work more with the ionosphere, but I suppose that if it is high resolution that you use for defining the cyclones, it's supposed to be high computational capabilities.
Absolutely. So you're, the word that I heard was assimilation, right? So you're, no kidding, you're going to take the data and assimilate it into a numerical weather prediction model and come out with a forecast. That takes a tremendous amount of computational power, right? But the, you know, the NOAA and NASA and the that are helping us with it have, you know, a lot of you know, supercomputer capacity to do that. But yeah, that's a big job.
So it's not like anyone can use this data for that. Okay,
Well, so it's very difficult to assimilate the data. So there are people that I'm aware of that are doing data assimilation, but with tropical cyclones, you know, that you need very fine spatial resolution, and you need a very small time step. And you need over, you know, a fairly large area, right? So it's almost, you know, bigger than mesoscale. So those three things taken together really drive up the computational load. If a user wanted to do, you know, a targeted study, I think they could probably do it with their, you know, with the cluster available to them at the university or whatever. But if you wanted to do, you know, kind of a mesoscale or even a mesoscale plus type of assimilation with very high spatial and temporal granularity, that really drives the computation quickly.
I just remembered the people that is listening to the talk that you are welcome to ask, and if you have any question, please write in the chat. We can read here and we can forward the question to Bill, okay? Marcos, please, do you have received something or have any other curiosity?
Okay, I wait for the audience, but I have many other questions. So let's move on. So you said that the data products will be available for the scientific communities, for the scientific community. Will be there a data sharing policy, special data sharing policy, and what data products will be available? In which level if you will deliver the analyzed and the data already treated, analyzed with the physical quantities that will be available? Or
Sure. So I think anyone can create an account on the. So NASA has a system they call Distributive Active Archive Centers, and we're going to be using the NASA Goddard version of it, something called the GES DISC, Data Information Systems computational resources. So you can make an account and download all the data from TROPICS. We will be putting out in the NASA parlance, they will call level 1 the brightness temperature data, the calibrated geolocated brightness temperature. So we'll have what we call the level 1B product that you will be able to get, and I think we'll put out the level 1A, which is prior to we have we geolocate it and absolutely calibrate it, and maybe you'll get it before there. If that's level 1B, I know you'll get level 1A. Maybe you'll get. If you send an email to me, I can get it for you. And then we have a level 2A product, which is trying to put the constellation elements on a similar grid and resample the resolutions of the temperature and the moisture to be on a common grid. That's our 2A product. Then we have a 2B product, which is all the profile data, all those 5 products, right? The profile data, the precipitation, and the intensity. And then we're talking about, so that's where our requirement stops. But we want to go beyond that. We want to do what's called a level 3 product, which is kind of a gridding over the entire globe of all the constellations. So we aspire to do that as well, but we're not required to do that. So that's kind of a best effort basis. So we'll be making, we'll make all our, we have what we call ATBDs, algorithm theoretical basis documents, and documents for the algorithm, how they're implemented. Those will be all publicly available. We'll be making available our validation campaign data. So our objective is to make all those data and even the metadata publicly available.
Yeah, that's great. That's great. I think when I see in your presentation the tracks from the cyclones, it's interesting to see that in Brazil there is only 1 or 2 tropical cyclones. We were hit by 2004 by one hurricane in Santa Catarina called Catarina. It made a huge mess in Santa Catarina, but of course I think people all over the world are interested in studying this. And I also read in your paper that we could also study, groups could study other meteorological phenomena such as monsoons and other meteorological phenomena. So it's very interesting to have this data available for the community. And
right.
Just a compliment for that question. Are you going to? I think you have already answered that, but I just want to be sure. Is that you have data available from all around the globe, or you have some kind of preference for having data from the American sector?
All around the globe. No preference. It'll be global.
Okay.
That's one of the advantages of the Leo constellation is we get all longitudes, and we will be putting all that data out there over ocean and over land too, by the way.
Okay, but I imagine that maybe you would turn off when you need to turn off. Then you turn off in another sector just to have the no. Okay.
We'll be on all the time.
Okay.
And I said,
I was just going to ask if the GPS data will be also available.
Yeah. So right. So all the let's see, the GPS data will have attitude data, the star tracker data. I think all that will be available too. And even some of the like the solar beta angles and all, I think we're going to have all kinds of stuff like that available.
Okay, that's nice. So there is opportunity to look for the top side or to the upper atmosphere also. Okay.
Well, let's see. With the we talking about with the GPS?
Yes. I mean, if you receive the data and you can do the positioning, but you have the phase and all the measurements.
Okay. Oh, you're talking about kind of the raw GPS data. Prior. Yeah. Okay. So that I don't know. That's a good question. I don't think that we have plans to release that just because nobody's ever asked us for it. But if you want it,
it's a good altitude of the satellite, 500 kilometers from a good place.
So yeah, I'll have to get back to you on that one. I'll answer your question, Ron. We have no plans to provide that, but I don't see any reason why we couldn't do it on a limited basis if you were interested. So.
I think we are here in my institute here in the LR. We would like.
Okay.
Mm-hmm.
Okay, so we have now a question from our audience from San Bitco. I read his question. One would expect only a handful of tropical storm cyclones per year. Do you have in mind any other practical applications of the observations while no storms are observed?
Good question. Good question. And so, by the way, so this year has been pretty crazy. I think just in the Atlantic Basin alone, we're on like Hurricane 26. So there's quite a few storms out there for that. But your question is still great. So we envision the tropics can do a lot more than just measure tropical cyclones. So we can certainly use it for synoptic weather forecasting. Same thing that we use the NOAA sounders for the day. Right, so we can measure the atmospheric state over the entire globe, within our orbital band. So there's a whole host of things that we can use that for. So I think one really neat application that we're going to bring to bear is diurnal cycle studies. Okay, because our satellites will not be in a sun-synchronous orbit, and all the NOAA and the UMETSat, all those satellites are sun-sync. So they have only a very limited set of diurnal measurements, whereas we're going to have a wide range of diurnal measurements. So that's what I'm very excited about, is our capability to make fine scale measurements of the diurnal cycle.
Okay, Fabrizio, did you receive any question from the audience?
Yeah, there is another question from Samtico also. He's asking if are there any particular type of storms that the observations will be focused more?
Well, so we're going to try to measure tropical cyclones from, when they're essentially from depression all the way through category, all over their life cycle. So they intensify as high as category 5, and dissipate. We're going to try to measure the entire life cycle cyclones. So the things where we have the relatively less sensitivity, or if there's a lot of ice in the clouds. I mentioned this in the talk. It hampers our ability to see below that ice. So storms where there's a lot of rain, if there's a convective storm, we don't have a lot of sensitivity underneath that convection because it perturbs our millimeter wave band so much. But we're going to try to measure all these things and see how well we do. But we expect we'll have our least sensitivity for those convective storms.
Thank you. Marco, how about your audience?
Okay, next question for the audience. What are the fields of application of the data collected by this satellite in agriculture science?
Yeah, okay, that's a great question, and so that very quickly evades my area of expertise. But so I should mention that we have a very vibrant applications user community, and we actually have what we call early adopters of our data, and we have applications workshops. We've got a couple of those. And we've had folks come to our meetings from the insurance sectors and commodity traders who want to use our data to measure. If we can measure rainfall, then we can start to predict flooding and some surface phenomena in terms of hydrology things that we can get second order from tropics. So those are some applications that we're trying to work in conjunction with other sensors and satellites and observations. So some of the hydrology, we can start to do a little bit of hydrology with tropics, but not very much. But we're learning more about what we might be able to do in concert with other types of instruments.
Okay, thanks. Here we have a question from Amalie Abraham. Beyond cyclones, forecast and monitoring, what other applications could the outputs as precipitation, soil moisture be used for?
Yeah, okay, so that's kind of related to the last question, where we're very excited about hydrological applications. So Cygnus, for example, was designed to be a tropical cyclone, wind measuring instruments, and they discovered they can make very good measurements of soil moisture from Cygnus, right? So I think there are some interesting applications where we can put together our measurements with Cygnus and do some really nice soil measurement. And of course, with sensors like SMAP and SMOS are great sensors for doing soil moisture. So I think there's a lot of headroom in the synergistic use of sensors like TROPICS and Cygnus and SMOS and SMAP that we're only now starting to explore. But hydrology, the answer to that question, I think there's a lot of cool hydrology applications here.
Mm-hmm.
Okay, we have another question here from Dmitry Vasiliev. can you detect the indications that a storm is going to be formed, or you are going to analyze only the already formed ones? Thank you.
Yeah, so the cyclogenesis is a really difficult thing for our instrument to detect. I mentioned the millimeter wave bands. So there are a lot of clouds and things when they form. We're going to try to see what we can do, but that will be, I think, one of our weaker areas is cyclogenesis. So I think that's going to be a reach goal for us. We're going to try, but we're not going to promise that we'll do very well with that. And has any ideas on how we might do better? We're just hampered by our lowest frequency is 90 gigahertz. So we need lower frequencies to do a good job with that.
Okay.
Okay, we have another question from Dimitri. Is there asymmetry in the time of occurrence of storms in the northern and southern hemispheres? More a general question.
Yeah, so that's interesting. You mean like if a storm forms in the south, is there a better probability that a storm will form in the north? Kind of a correlation type. I'm not sure. That's a good question. I don't know off the top of my head if there is a symmetry in the north and the south. It's something we can go out and look at, but I don't know. It's a good question.
I will read a question from Marcos, a colleague of Brazil. And he asks, in your point of view, since the audience here consists of young professionals, is there any initiative to promote the usage of these unique data sets to support research? What about bachelor, master, and thesis contexts?
Yes. Okay. Fantastic. I'm glad you asked. So so I mentioned the user applications community. We certainly want to get folks involved there. And NASA has some initiatives where they have calls for international partnerships to use NASA data, and that would certainly qualify there. So we're very interested in educational uses and opportunities to use the data for young scientists. That's a big thrust of ours. So we are totally behind that one, and I think there are a number of formal mechanisms to get involved. And if you have any specific things, you can certainly email me or anyone from NASA, and I'm willing to help and see how we might be able to connect. But I think that's a great idea. We fully support that.
Thank you.
Okay. I have another question from Amalia Abraham. Any plans to improve the spatial resolution, or does it have any correlation with the system performance?
Yeah, so given that we have a fixed antenna size, the only way we can improve the spatial resolution is if we can fly in a lower orbit, right? So over the course of the mission, our satellites are gradually going to deorbit over the course of about 5 or 6 or 7 years. So we're going to get better spatial resolution as the satellites deorbit, but we're not really planning on doing anything as part of the mission for that.
Okay, we have stopped a bit the web chat, but I have one last question, or it's just a comment that if you could include some comment related to the advantages and disadvantages with the side GNSS. There are some obvious advantages.
What? I'm sorry, could you repeat that?
If you could include some comments related to the advantages and disadvantages in comparison to the side GNSS. The side.
The Cygnus mission, the Cygnus.
Yeah.
Yeah. Oh, okay. That's okay. Yes. Very okay. So the Cygnus mission, it's very interesting how Cygnus and TROPICS are complementary. So Cygnus is trying to measure the wind speed over the ocean surface. Okay. So they measure the wave heights and how that correlates to wind speed over the ocean. So that gives you wind. But it doesn't give you the thermodynamic structure inside the storm. So what TROPICS is, so Cygnus is kind of looking from the bottom of the storm up. TROPICS is looking from the top of the storm down. We're trying to figure out what's going on in the top of the storm. Moisture, temperature, precipitation, from the top down. So we're coming at it from different perspectives vertically. I think is the easiest way to think about it.
Okay. Not.
Marco, ¿você recebeu alguma pergunta? Marco, did you receive any question from the audience?
No. No. For the others, no.
No? Okay.
No. But if you want, I have more questions. I can.
No,
think
okay.
you can.
Okay. If you want, you can ask something.
Okay.
Just to say that we are reaching the end of the timetable. So
I'll try a short question.
Use it.
So I'm involved in the science team of another NASA mission, which is a mission in partnership with Brazilian institutions. And I see from the engineering team that there are many risks. And I see in your, I was looking for the issue of the rotating axis, and I was imagining if that could be a source of problems. So my question is, what are the major risks do you see do you are anticipating in your in TROPICS mission?
I had a little trouble hearing the last part of that question. I think my computer
just the risks. What is the major risk, engineering risk you see in your
right. So the things we worry most about are the mechanisms, the things that are moving, the hardware. So the motors that drive the arrays, the reaction wheels, the motors that turn the payload, the slip rings. Those are the number one risk, is all those things that move. Second risk is electronics, radiation effects, single event things. That's the second category. And the third category is the battery. So we have a limited life of the number of times we can charge and discharge the battery. And then there's a whole litany of things underneath that having to do with memory cards and so forth. The microprocessors and the controllers and all that stuff.
Okay. Thank you for sharing.
Okay, I will just make one last question. This is the last question, and I want to put clear to the audience. If you have more questions, normally at the beginning, the questions are very rare, but at the end, there are coming a lot of questions and we cannot answer everything. So you can formalize the questions, you can put it, write it in the chat. We will forward to Professor Bill and we will try to answer all the questions, but we have no time now, right now. So the last question is from Amir Oliveira, and he asks, since the space resolution for temperature profiling is about 24 kilometers, if you have a mesoscale connectivity system with thickness of about 10 kilometers, what would it look like in the images?
Yeah, so we would really love to be able to measure mesoscale convective systems. Our resolution, as you point out in your question, just isn't good enough. So what will happen is that it will get blurred out in the image. Okay? So it'll get attenuated and smeared out over the course of the image if we have a sub-pixel measurement of that. So there's really nothing we can do to improve that.
Okay, and so please feel free to ask, write your questions, and we will try to answer everything. And now we are unluckily we reached the timetable, and I am very glad to see that there are many questions that are being written now. The theme is very interesting, but we have no time. William Blackwell, thank you very much for being here and giving us such a lecture that we don't have the opportunity to see every day. And I think this is a very interesting topic, especially for these future researchers, these young professionals that will face in the future even more and more these small satellites. And as I read about these mini satellites, I didn't believe at the beginning till I saw some papers, and it's really very interesting. And we are tempted to develop. It's like the drones. No? We want to have one. It's not so expensive like the bigger ones. And I think this is a field of research with future for us, and this is very good for this special event. And I would also ask Marco Ridenti and Fabrizio Prol for the support that they give us, and also with the question that helped us to clarify the theme. Do you have something to say, William, before we close this event?
Well, I just want to say thank you very much for the invitation. It's my pleasure to talk, and the questions were all fantastic, and I'm certainly happy to answer any questions that come up or make any connections. There's a couple of questions that maybe I can help with to maybe connect some folks. Happy to do that, and best wishes to you all. Thanks very much for the invitation. I really enjoyed it.
Okay, thank you. And again, Marco, Fabricio, thank you very much. This is a worldwide conference with Fabricio is in Germany, USA, in Brazil, everywhere here. And I'm very happy that the internet is giving us these opportunities. As I was a young researcher, I just had Telnet and FTP, and that was the biggest thing we had. And now we can see face and talk online. This is wonderful how times are changing. Thank you again. Thank you, everybody, for being here. And in the name of the ISPRS and GRSS, I'd like to thank everyone for the participation. So Bill, Fabricio, and Marco, see you. See you also, everybody.
See you. Bye-bye. Thank you very much.
Bye-bye. Thank you.